Great to see everyone and great to see everyone scattered all over the world. So thanks to the people who are attending, especially at odd hours. So in some ways, I find that it's been getting harder and harder lately to give these talks on sort of machine learning and causal inference relative to when I first started working on the problem. And part of that is, when I first started working on it, there wasn't that much work that related, you know, theories of estimation and theories of identification with the recent advances in machine learning. More recently, there's actually an explosion of work. And so it's actually hard for me or anyone to even keep up. Nonetheless, today I'm going to sort of I'm going to sort of start a little closer to the beginning and talk about the first work that I've done in this area. But I just want to highlight that the area is moving very quickly, and there are a lot of kind of frontier questions that I won't even be able to get close to. And also, I want to highlight something that I've been emphasizing in a lot of my kind of keynotes recently for machine learning audiences, that there's more than one type of causal inference in economics, and more than one kind of approach to causal inference in economics. So today I'll be talking to the one that I found the easiest to connect to straight supervised machine learning. But I just want to highlight for you, there is a wider world of causal modeling in economics. For example, some of my other research is working on trying to estimate price sensitivity for consumers when they're making choices when shopping in the supermarket, and use those models to optimize a firm's pricing decision. I have also done work on auctions where I've used auction data to try to estimate from from bidder behavior, their preferences, and then use those estimates to try to optimize market design. So using models sort of for design and optimization is another big branch of economics, and also operations research. And some level, we're sort of moving both closer to that in my own research now, but also I think from a research perspective, there's actually like a wide range of generative models. And so I think one thing that all that shares in common, though, is that we think about how the data is generated. We think about whether it's even possible to learn what's needed to do a counterfactual, and then things start to get more rich and complicated. As well, how do we estimate these models? How do we translate a problem where, in principle, we could figure out what we need to know from the data to a strategy, an empirical strategy for actually carrying that out? So that's kind of just a high level advertisement that there's a wide world out there. But I'm going to start today sort of closer to, I think, what you've been talking about and where a lot of the work has been to date. And off to the races. Does that look good now?
Yeah, it looks all good.
Perfect. All right. I really did restart like half an hour ago. So sometimes these things happen. Okay. So I'm going to talk about heterogeneous treatment effects. And so heterogeneous treatment effects come up when you're trying to evaluate the impact of a treatment. The applications can be things like evaluating A/B tests, and actually a number of tech firms, which is always very exciting for me, have told me how they've implemented some of my methods in their A/B testing platform. And it's especially exciting because that was actually one of my original motivations. I used to be chief economist at Microsoft, and I worked on the Bing platform right when they were first trying to figure out how to even set up A/B testing for their advertising platform. And so one of the things that I noticed was that they would make a lot of decisions about whether to ship an algorithm based on the overall aggregate performance of the algorithm. And actually, the people who guarded the A/B testing platform would say, oh, we don't want people to be able to data mine our A/B tests. And the reason they didn't want to let them do that is that if you think about an engineer, they get a bonus if something ships. And if it looks like their experiment didn't pass the A/B testing, it would be very tempting to go out and search through all the different subgroups in the data until you found one where it worked well, and then say, hey guys, look, it works well over here. So please release my new algorithm, just on these people over here. And they were worried about this sort of ex post mining of the data, which would find something spurious that wouldn't replicate if you ran the experiment again. So generally, people wanted to, I think people recognized that it could be valuable to understand heterogeneous treatment effects, but they felt like it was important to guard against that kind of snooping. And that same kind of concern also comes up in a drug trial. So suppose that, you really wanted your drug to be approved. The average treatment effect of the drug in the trial looks like 0. And you look around in the data and you keep looking at all the different characteristics of people, and finally you say, for women between age 50 and 55 who have these 3 pre-existing conditions, it looks like my drug works great. Because you peeked at the data to try to find that group, your results are unlikely to replicate. So generally, that's why in experimental design, both in companies and in medicine, you have to register your experiment in advance. And if you plan to test any hypotheses, you want to state those in advance. When we haven't done that in fields like psychology and parts of economics and so on, you have these replication crises where people post results from experiments that can't be replicated. So the goal is to try to figure out how to estimate heterogeneous treatment effects without coming up with spurious results and finding results that can replicate. And if it's something like the FDA or even a rigorous A/B testing platform for a firm, you want to make sure that your results are reliable, and you want to make statements about uncertainty as well. So just to motivate, the confidence intervals, you might think, oh gosh, tech firms have lots of data, so why would you care about expressing uncertainty? But in fact, most tech firms are currently optimizing. And so if you walk in as an intern and say, hey, I got this great new idea to make Google better, the chances are that you can't, or the effect will be very low. And especially if you're trying to learn, how does some new treatment work for some people rather than others, actually the effect sizes are often small relative to the noise. So even for Google, even for Bing, you still have trouble finding signal when for new treatment effects, and especially when there's noise. And so it's important that you have a way to express whether the result you found is just spurious and sampling variation, or whether it's a real effect. And so the challenges here are twofold. Then I want to use modern machine learning, if possible, to find heterogeneous treatment effects, but I want to do it in a way that's replicable and reliable and allows us to express uncertainty. Other motivations for doing heterogeneous treatment effects, so just broadly, how would you use those results? One is to systematically identify subpopulations to say, these people should get the drug and these people should not get the drug, or I want to release my algorithm for this group of people. You might also want to understand the mechanisms. So if an engineer releases a new algorithm, I want to understand, well, how does that work? And knowing for whom it works gives you a lot of intuition about how it works. And especially if you're in an environment for doing ongoing innovation, that can be helpful. Similarly, if you're a behavioral scientist, and I'm working on an experiment now around fake news, we're going to give interventions to try to get people to stop sharing fake news. If I want to know why it works, it's helpful to know for whom does it work. So if I know that it works well for highly educated older people, that already helps me narrow down the set of mechanisms by which the treatment works. And that can also help me then design the next experiment. On the other hand, if it doesn't work for a certain group, then maybe I need to go back to the drawing board and come up with a different kind of treatment. So it's important both for I would call that understanding mechanisms is really scientific understanding. And that's where we really care about the heterogeneity itself. And then the second goal is, well, I just want to make a decision and I want to decide who gets treated. So this idea of making a decision is what we call like optimal policies. So so the optimal policies are different. The objective of optimizing an optimal policy is different from heterogeneous treatment effects in some core ways. So just as an example, I might have a drug that works better for the control than the control for, say, everybody over 60. It might work even better for older people than it does for people in the 60. So it might work even better for the 70 plus people than the 60 to 70 people. But if it works well for both, My policy is they should both get the treatment. So I don't really care to distinguish how well it works. I just want to know that it works. On the other hand, if I'm trying to come up with mechanisms or figure out, where should I guide, how should I do new drug discovery, or where should I invest further in the future in innovation, then it really matters that who it works amazingly well for and who it works just a little bit well for. So these are really different scientific objectives, different statistical objectives as a result. Even within the optimal policy space, there are different kinds of questions you can ask. So I might, in some settings, need to have a fairly simple treatment assignment rule that's customized to subpopulations. Even in the tech firm case, there's a cost in terms of milliseconds of response time, as well as coding and maintaining code. If a person comes in and I have to actually call an algorithm and have a function call that evaluates something and then returns the result for that individual, it's actually going to be much faster if I just have a lookup table that says, okay, is this person in this segment? I can just write a case statement that says, if A, then do this, if B, then do this, if C, then do this. And if it's a simple case statement, it'll evaluate more quickly, be easier to maintain, also easier to evaluate and monitor over time across those segments. If I'm trying to define a treatment assignment rule for doctors or polices, they might need to memorize things. Like, here's the situation where you do X, or an ambulance technician might need to memorize a set of rules. We might also need to post on a website, here are the eligibility criteria, and I might need to display a tree that says, well, if you have this, income or this former test score, you would be eligible. So I might need to come up with a simple rule. In other cases, I might be able to do something that's customized to an individual. So if I'm doing sort of computer-aided decision-making where I'm going to be able to put all the data in and get a recommendation back out, I could have a very complex decision rule, one that's difficult to describe. So if I'm in a doctor's office and I've got an algorithm that looks at all of your information and then comes back and says, here's the recommended drug, the doctor doesn't need to understand why it works any more than they need to understand why laboratory tests work. They just need to know, here's the recommendation, and can I trust the overall system? Is the overall system effective? So in different settings, you might have different, values and constraints that would lead you to estimate a simpler or more rich assignment rule. So big picture from the slide is something I think it can be really confusing when you try to read the literature with papers one by one. And there's this whole bucket of like heterogeneous treatment effects, and you don't really know why you're doing what you're doing. So I just want you to take from this that actually you should start with your goal and then choose the appropriate method and question for your goal. Once you understand that, you also should ask yourself, is the method I'm using optimized for my goal? And the great thing about machine learning is that you can specify your objective functions and optimize for them. And so, you want to make sure that you've thought through exactly how those line up to get the best results. So, I'm sure you've all, coming from machine learning, you've studied one of the simplest machine learning models, regression trees, where you partition the data. So this is an example, X1, X2. In a traditional regression tree, what you would do is try to separate the data according to to make the outcomes similar within a box. So, if you want to find rectangles where everybody has a success, or rectangles where everyone has a failure. And this is an example of supervised machine learning where the objective is just to optimize goodness of fit. One of the things about when you optimize this, you would do something like cross-validation to determine the depth of the tree. You have an objective for that cross-validation. And, and so when you do that cross-validation, you're trying to optimize goodness of fit. You can hold out either a test set or a fold that's used for cross-validation, estimate a model on part of the data, predict on the other part of the data, and see how well you did. That's a core tenet of supervised machine learning. One of the first challenges we faced in trying to bring supervised machine learning techniques into causal inference is that for causal inference problems, you don't actually observe the ground truth in the test set. So we're not all walking around stamped on our head, what's my treatment effect of the drug? And if you put me in a test set, you wouldn't know for me individually what's the treatment effect. for me. And so if you predicted that I had a high treatment effect in the test set, you wouldn't be able to evaluate whether I did or didn't. So we had to figure out ways to overcome that. And the TLDR on that is that it actually for different settings, we've come up with different objectives that can be estimated in a test set. But in general, you're going to have to do some averaging in the test set in order to assess the quality of your predictions. It's difficult to do it sort of one at a time. So the first paper that we worked on here, and it's kind of funny because when I started writing this paper, I didn't actually know nearly as much about machine learning now, and there was a lot of the theory that hadn't been worked out. But the funny thing is, this is still one of the most popular algorithms that we've come up with. It's very, very simple, and it's one of the things that tech firms implement. But it was also, again, inspired by what seemed to make the most sense for this category of applications. So the idea of causal trees is to do regression trees, but where your objective is to optimize for heterogeneous treatment effects. And just to highlight why heterogeneous treatment effects is a different objective than supervised learning, there are many, many situations where the factors that would predict outcomes are different than the factors that predict treatment effect heterogeneity. So, for example, your parents' income and education is going to be highly predictive of your educational achievement. And in a big university, richer people with more educated parents might be more likely to do well, in a course. But the factors that make, say, a flipped classroom better than an in-person classroom might be different than parents' income and education. It might have to do with the way that you process information. And so if I want to think about the treatment effect of having an in-person class versus a flipped class, it might not be the same factors that relate to the level of performance. And so if I trained a supervised learning model just trying to predict your outcomes, it would load up on the factors that predict outcomes. Well, it might be a completely different set of covariates about your learning style that affect, whether you do better or worse with being able to view videos at your own pace versus have to go with the pace of that annoying instructor and deal with their technical problems. So so it's a different objective. We want to, and in a case where we have limited power, it matters how you split your trees. If you had tons of data and you wouldn't really, the objective wouldn't matter much. You can split on both characteristics, and eventually you split on everything. But if you have more limited power, these trade-offs make a difference. So we would argue that our goal for heterogeneous treatment effects would be to create subgroups that are, say, one group that has high treatment effects and other groups that have low treatment effects. And so my goal might be the mean squared error of treatment effects. I might take the expectation over a test sample of the squared loss, which would be the difference between an individual's treatment effect and their predicted treatment effect. Now, the problem with that is, as I said, this tau I is unobserved. So we don't, unlike if this was a Y, if this was an outcome, this would just be something we could read off the data. But instead, tau I is unobserved. This is an infeasible criteria. And so in all of these different papers, a lot of what we boil down to is, well, what's a good operational criteria we can use in place of this infeasible criteria? For the case of trees, the problem is actually relatively simple, because in the end, this tau hat is going to be constant within each leaf. Because it's constant within each leaf, then this squared loss will basically just have three terms. One is the tau I squared, but that's just a constant. For any different estimator tau hat, the tau I squared would be the same in each case. So I don't actually need to estimate tau I squared. And then the second term would be a tau I times tau hat, like this is the minus 2 times tau hat times tau I. But since tau hat is actually going to be constant within a leaf, then in the end, to estimate this objective, I'll just need to know something about the average value of tau I within a leaf, because it's going to be multiplied by something that's constant within a leaf. So that's actually a fairly simple problem. And so we can do a pretty good job estimating this objective for any given tree. Now, in cases where that's not the case, where our tau hat isn't constant over a group, there are other ways to go about this. And in various papers, we propose different objectives. And then my co-author, Stefan Wager, has a separate paper with something which he calls the R-learner objective. So they're not having that be constant is not a deal breaker. It's just it makes it particularly simple in this case, which is one reason in a longer class I like to start with this, because you can actually just directly derive how to estimate this objective. So a second thing that we wanted to think about in this paper, though, is that we worry about data snooping and data mining, like that we're going to look at our data and find spurious results. And so our solution to that, and this is something where my first idea, I thought there must be 10 better ways to do this, but it turned out the first idea actually may be relatively the best idea. It's actually hard to improve on this, is some kind of data splitting. And so basically what we want to do is split the sample and find the heterogeneity on half the sample, and then estimate the heterogeneous treatment effects on the other part of the sample. And what that's going to do is it's going to avoid this case where we might overfit to an outlier. So in principle, like if Brady had like a very high outcome, then if he has a high outcome, it's also going to look like he has a high treatment effect. And so I might want to find all the characteristics about him, like, people, men of an age with glasses, and I find enough characteristics about him, and then I find some other people like him, treated in control, who have average outcomes. And then that group is going to look like if he's treated, the group is going to look like it has high treatment effect. And if he's control, it's going to look like it has, a negative treatment effect. Because if I just have one guy or a couple of guys with high outcomes, I'll build a group around them, and I'll find the things they have in common. And the way it looks at this, this machine learning algorithm can find the 4 or 5 people with the highest outcomes. If there's 4 or 5 treated people with high outcomes, I'll build a group around them. I can find something they have in common, and then it's going to look like there are high treatment effects for that group. But if I went to another sample, I wouldn't replicate that. And so that's what I'm concerned about. And so the data splitting helps with that. The cost is that it means that you're going to build a shallower tree and have less personalized predictions. But the benefit is that you'll have valid confidence intervals for your results with coverage rates that do not deteriorate as the data generating process gets more complex or as more covariates are added. And that's basically because you'll do cross-validation. You'll build a tree that is not too deep. And then as long as you've defined groups, if you've defined those groups in one part of the data, I can test whatever hypothesis I want about those groups in the other part of the data. And as long as there's, 30 observations in the treated and control group in each leaf, the law of large numbers kicks in, and I can just do standard asymptotics. And so one reason I think that this is appealing to both A/B testing people and to social scientists and others, and medical people, biostatisticians, is that they don't have to make any theoretical arguments. It's just completely clear that you can test hypotheses in a valid way from this. So there's no arguing with your referees or your reviewers. It's just obvious that it works. And again, it doesn't require any assumptions on the data generating process other than that it's a randomized experiment, or we'll come back to unconfoundedness. And it doesn't require any asymptotic theory other than having enough observations in each leaf. So let me just give an example of this that shows the importance of data splitting. This is an experiment I ran on the Bing search engine, where in the context of an antitrust investigation against Google, we re-ranked search results to try to see the effect of manipulation. So in this experiment, we took the first result and the third result and flipped them. So the control group had the results ranked in the normal order. The treatment group, the first and third result were flipped. And what we're looking at is the treatment effect on that first result in terms of clicks. So how many fewer clicks does the result get when I take it to the third position? And then the characteristics are the characteristics of the search query. So is the query about celebrities? Does it look like it's an image? Is it a navigational query? Does it have something to do with Wikipedia references and so on? And so the average treatment effect was about minus 0.125, which would say that, that's on a scale of 0 to 1, it's saying that you're losing about a 12% of your 12 percentage points on the click-through rate, which is about half your clicks. So on average from that manipulation. But we find that in some boxes, the average treatment effect is almost close to zero. Like image celebrity queries, manipulating the results didn't matter. And that's basically because, like, if you're trying to look for a picture of Britney Spears, then, you click on the picture of Britney Spears and it doesn't really matter, what the other results are about. While things that were classified to be high on Wikipedia reference had larger than average treatment effects. And we see the proportion of the observations in each box and the standard errors. And you can see how a tree like this would help you kind of gain insight about where manipulation might be important or not. And this is the rest of the tree. Now, what I want to show here, and actually it's easier to show it in a picture, is that what I've done here is I've said there's a bunch of leaves in the tree. So each of these pairs of bars corresponds to a leaf in the tree. And I've ordered them in order of the magnitude of the estimated treatment effect in the half of the sample I use to create the subgroups. So if I use the same data to create the subgroups and then do the estimation, I would get the blue results. And these are expressed in terms of deviation from the average treatment effect. So this first blue bar would say that, I've got a leaf where the deviation of the average treatment effect is minus 0.15. Remember that the average treatment effect was about 0.125. So that's a very large deviation from the average. On the other hand, the orange bars are closer to zero. And that's showing that when I take those leaves that were created in one part of the sample and I go to the other part of the sample and I estimate average treatment effects for each of those leaves, I get more moderate results. I get results that are closer to the average. And that's what you expect if you're overfitting to the original training data. Now, one reason I use this example is this experiment had about 800,000 queries in it and about 20 leaves. So it would seem like that these overfitting considerations wouldn't be there. But there's also a lot of covariates, and the machine learning algorithm has lots and lots of ways to create different partitions. And so it's basically saying even with very large data sets, you still have to worry about this problem. So that's one reason that some form of sample splitting, and I'll come to cross-fitting later, is something to really think hard about if you're ever trying to do inference. If you wanted to say, hey, this particular leaf is different than the average, and I think we should do something about it, and it's not spurious, then sample splitting is going to be a much more credible way to illustrate that. Okay, so let me pause there. Any questions on that? And I think I would just say that, this is not the kind of thing that you think about in machine learning a lot, because a lot of times you're not testing hypotheses. So this idea that you would throw half the data away sounds kind of crazy. Like we've been doing, regression trees for 30 years. We haven't been throwing away half the data before. But here now I'm asking about, I want to get unbiased estimates of something and test hypotheses. And that's where this would matter. Yeah. Did you have a question, Brady? Or did someone have a question?
Well, I don't see any in the chat yet, but I do have a question. It was just about, you mentioned that there's no arguing with your reviewers in one bit. It kind of fixes having to argue with your reviewers. I think it was around large numbers or central limit theorem or something. What was that part?
Sure. So basically, in the results I'm going to show you next about causal forests, then, we have a theorem that says as n goes to infinity, under these conditions on the data generating function, you can get a personalized estimate and put a confidence interval around them. But if you're trying to do non-parametric estimation, so I'm trying to get an unbiased estimate for you, Brady, with glasses and, a man of a certain height and everything else about you, the fact is that I'm probably not going to have a lot of data about people just like you. You're unique. You're a special flower. And I can't find, a large group of people just like you. But if I think about, so even though asymptotically I can get a good confidence interval for you, the coverage might be bad, and you might need a lot of data to get there. In this causal tree kind of setting, we're going to take half the data to construct the subgroups. But then on the other half of the data, if I have 10 subgroups, I just have 10 numbers I'm estimating. I'm not actually trying anymore to estimate the full tau of X surface. And so to estimate those 10 numbers, I don't need that much data. And in fact, if I say if one of my subgroups is men over 65, if God gave you that group and said, here's a data set with, 10,000 people, tell me the treatment, and I have a randomized experiment, tell me the treatment effect for the men over 65, all I need to have is like 30 men in the treatment group and 30 men in the control group. In that segment, and I can just take the simple averages. And so the statistics around, when can I test a hypothesis using a difference of means are very simple. Like I just need the law of large numbers to kick in for 2 sample means in the normal distributions. So it's completely transparent. And the only complicated part was that we used a data-driven subgroup, but because we chose that subgroup in a different data set, there's nothing different in how I apply that in the second separate data set.
Sounds good. Great. And there are two quick questions. I think they're fast questions. One is, can you use trees to do individual treatment effect estimation? And then
I'm going to talk about that next. And yes, you are trading off because when you do this sample splitting, you're basically, you're getting a smaller sample, and you're not going to be, but you're not going to be able, you lose mean squared error because you're going to be using less data. You won't be able to have an expressive a model. So losing half the data hurts both bias and variance from that perspective. But it allows you to get consistent estimates with a good confidence interval. So honest estimation, we split the data. We take half the data to select the model. Like if we were running a lasso regression, it would be like using half the data to cross-validate and then figure out what variables go in the regression, and then taking the other half of the data and just estimating a simple regression with the selected coefficients. In this case, we're using half the data to build a tree and cross-validate the tree. And then once you know the leaves, you go to the other half of the data and you estimate the effects in those leaves. And so in a randomized experiment, within each leaf, you're just going to estimate a treatment effect, simple averages, treated versus control. I'm not going to talk now about how you would do it in an unconfounded experiment, but we'll come back to that. And honestly, though, if you have unconfoundedness, the trees are a little bit less elegant because it can be harder to do it well. Okay, how do you do with highly unbalanced data? Well, that's one of the reasons it was helpful to write dedicated software, because we do want the splitting to take into account that you need enough treated and control observation in each leaf. And so our splitting has 2 ways to do it. First of all, we just force there to be enough treated and control in each leaf. But second, we also have a criteria. Part of the criteria that we use for optimization incorporate the fact that if you start having very few treated in a leaf, you're going to have a very high variance estimate, and that's going to be bad for the performance for our criteria function. So our criteria function will penalize a leaf that doesn't give you a good estimate. So you have to look at the paper for more details about that. Okay, so let me move on though to doing an individual, a more personalized treatment effect. And again, we have to be careful with the language here. It's still a conditional average treatment effect, conditional on your X's, but now I want to do it conditional on a single X rather than on a subgroup. So when we go from trees to random forests, well, for a predictive model, the forest idea is just you build a bunch of trees and you average up the predictions. You average them up by either bagging or subsampling the training. Bagging is sampling with replacement, and subsampling is just taking a subsample of the data. It turns out that from a predictive perspective, it doesn't really matter that much whether you subsample or choose a bootstrap sample. But from a theoretical perspective, subsampling is going to be much better. Why is it much better? Well, it's going to be much better because as long as I'm subsampling, I might as well subsample twice. So I might as well subsample one sample to build a tree and subsample a second sample that doesn't overlap to estimate the treatment effects or make the predictions within the leaf. And so we actually show that even for a predictive model, that subsampling and doing honest subsampling, so taking one section to determine the structure of the tree and a second subsample to do predictions, can perform better in a variety of contexts. Not always, because there's some context where you're really sort of short on data and you really want to use all of your data to build a very expressive tree. Like if there's a very strong signal, then you're not going to make any mistakes and you just want it to be expressive as possible. But in an environment where there's more noise and you're more likely to make mistakes, and be prone to sort of overfitting considerations, then this honesty can work a lot better. It also can work better on the boundaries. It has a variety of properties. So causal forests are what we propose in this JASA paper. We use subsampling to create alternative trees, plus a lower bound on the probability each feature is sampled. The causal tree has splitting based on treatment effects, and we estimate treatment effects within the leaves. And it's going to be honest because we're going to have two subsamples, one for tree construction and one for estimating the treatment effect at each leaf. And then we're going to output predictions for tau of X. So since the accuracy of the treatment effects, again, can't be directly verified during a test set, the statistical inference is going to be crucial. For that end, we're trying to achieve asymptotic normality. So we would like our estimates to converge to the truth. And we'd also like to be able to do confidence intervals. And so those are the things that we work on in the paper. I should say that actually it turned out to be easier to show asymptotic normality than it is to show that you're centered on the truth. And what was one of the things that was important about our paper is that we could do both. We could show that, tau of X converges to tau and you're asymptotically normal. So I'm not going to give you all the theory of that today. I think it's hard to do that in an overview lecture. So you'll need to dig into that. I should mention that I have much longer tutorials on my that are available. I have longer videos, longer tutorials, longer slide sets. So if you want to dig into those details, one of the easiest ways to get to it, if you just Google Susan Athey Machine Learning AEA, that's for American Economic Association, you can find a link to a drive that has lots of that material. And I'm working on a website. I know it should just be on my website, but I work in a business school where they won't let me build my own website and take a year to put things up. So apologies for that. So that's what we're trying to do. And then let me now show you some examples of applying this method so you kind of get a sense of what you could see out of it. So before I showed you a causal tree that had subsets and treatment effects, now I'm going to be plotting treatment effects that can vary continuously with the covariates. So in this case, there was a randomized experiment of asking people questions about their political beliefs or their beliefs about social issues. So treatment A was, you said, hey, how do you feel about assistance for the poor? Treatment B was, how do you feel about welfare? Now, if you're not from the US, you might not know that those are the same thing. Welfare is assistance for the poor. But there's been a lot of branding and language around welfare. Well, welfare is bad and it's for lazy people, while assistance to the poor doesn't have that same connotation. And so the experiment was going to determine how much more did people like assistance for the poor framing than the welfare framing. And this is basically the outcome is about whether you're in favor or not. And we see that there's actually very large treatment effects. So, 25 percentage point increase in whether you like assistance to the poor relative to welfare. But the effects are even, that's for the most liberal and least rich people in the sample. But the effects are substantially larger, closer to 40 percentage points for the people who are most conservative and have the highest income. And in the paper, we were able to test the hypothesis that those are in fact different. But so the idea here is that, if you estimate these causal forests, you can do heat maps like this and try to just let the data tell you where the treatment effect heterogeneity lies. And the fact that we've used honest estimation means that we can trust it. So another example I'm working on now, I haven't published this yet, but soon, we're working on a retirement reform in Denmark. And in this case, it used to be that you could retire early and get retirement benefits. And then over a period of years, they made you have to be older and older and older to get these early retirement benefits. And so you can see that on the y-axis is what employment rates are. And for the oldest people, they had access to the program. And so as soon as they hit the age 60, the employment rate in that cohort went way down. But later, they didn't have access to those benefits, and so a lot of people kept working until they were 62. Now, we started looking for treatment effect heterogeneity in this group, and we have administrative data from Denmark. So we basically have all people in Denmark and everything about them and about their spouses and about their children and about their healthcare and about their benefits for like their whole lives, because that's what you do in Scandinavia, which makes it easy to do research if you get access to this data, which of course is closely guarded and carefully protected. So I have collaborators in Denmark working with the data. And so one of the things we see here is that for people with they're uneducated on the left, there's a lot of them were retiring early before and are thus very affected by the reform. While people with a master's degree were not retiring early to start with and were more likely to be employed, and the treatment effects of the reform are thus much lower. They were working anyways and they kept working. Here's another example from income. And again, lower income people were often retiring while higher income people were not. And that might be a little counterproductive because you give up a lot if you're high income and you retire. But of course, the jobs of low income people are also less attractive. So we also look at like characteristics of the job. So then we apply the machine learning to this to try to understand generally what's the treatment effect heterogeneity look like. And we compare using random forest. We call generalized random forest is our general causal forest algorithm. And we see the blue is the histogram of estimated treatment effects with that versus an ordinarily squares regression when we get similar results from a lasso in the peach. And so this is showing one of the advantages of the causal forest is that it does a better job fitting the functional form, and it doesn't sort of accidentally extrapolate people to have negative treatment effects when we know that in general the treatment effects would be positive. And here we're saying a positive treatment effect means that you're likely to work. And you can see that all of our predictions are positive, and it's intuitive that, you know, being taken away a retirement benefit shouldn't make you more likely to retire. We also can see that our model, we can look at the calibration of the model and in order to assess whether it's performing well. And so in addition to using statistical theory, we can also try to go directly to a test set to assess its performance. But one of the things that I highlighted before was that, well, I thought you said we don't observe things directly in a test set. We don't observe things directly in a test set for any individual. But so then a tactic you can use to assess the calibration of a causal model is to use your model to put people into groups. So here we've put people into 5 groups according to the quintile of their treatment effect. Then we go to a test set and we assess using standard causal inference tools, and here observational tools, like we're using doubly robust treatment effect estimation tools under unconfoundedness. We estimate what is the treatment effect in a test set for the people that we assigned to be in based on their covariates, the high treatment effect group. And we see that our model is in fact able to separate out people according to what we estimate in the test set. I want to highlight, we can't test our unconfoundedness assumption. We made it in the training data, we made the unconfoundedness in our test data. So what we're really assessing is whether our model is under the unconfounded assumption, are we distinguishing people with high treatment effects from low treatment effects? Is our model just spuriously saying, hey, you look high, you look low, but it's not accurate, versus have we actually achieved our goal in the test set? So the first way is to put confidence intervals around them. But if you're worried about sample size and asymptotics, the second way is just to put people into groups and then calculate their average treatment effect in a test set. It doesn't test your assumptions about unconfoundedness. It's testing the performance of your model at personalization. And it's sort of assessing whether your asymptotics actually have kicked in and make sense. But this type of exercise is crucial when you're estimating heterogeneous treatment effects, and I do this kind of exercise with all of my papers now. Then another thing we can do is we can try to look at the differences in the characteristics of people who have high and low treatment effects. So here, just to see the kinds of things we do with the output, we can say, okay, here are people that our model says are high treatment effect. There's a high share of employee in the people that had the highest treatment effects, and there's low share of managers. So again, the same managers keep working, but employees quit if they have the opportunity. And then we also see again that people who are high wealth, high income are less affected, partly because they just keep working no matter what, while it's the low-income people who apparently don't like their jobs and try to quit as soon as they can, as long as they have benefits to support them. Okay, so we're coming close to the end. Let me say, I'm not too surprised, but I didn't have much time to talk about estimating treatment assignment policies. I'll share the slides for this, and I have some notes about that. And then also, if you go back to my Google Drive, you can see longer sets of lecture notes around that. And I also want to remind you that I have tutorials available as well. R scripts, I have a GitHub full of data sets, so you can take my tutorials and run them on data sets, experimental data sets, and observational data sets I have available in my public GitHub that will allow you to test out some of these methods. So let me pause there and take questions.
The first question is just about the link to your drive, which, yeah, we'll post that.
Yeah, sorry, I should have put that up beforehand. I'll find it while other people are asking questions if they have any.
Looks like Jeremy's already put a link to some drive folder.
Great. Okay. Wonderful. And then I can also add in, this is a link to, this is actually pretty outdated now already, I guess, because things move fast. So this was January of 2018, but there's also 2 days of videos there as well. So what did the heat map allow us to conclude on the experience of welfare and assistance to the poor? So the heat map was basically saying that rich people and conservative people are happy to give assistance to the poor, but they don't like welfare. While poor people and liberal people also feel that way, but less strongly. And so again, the treatment was which way were you asked the question? And the heat map was showing the magnitude of the treatment effects. And it was saying that the treatment effects were larger for conservative and rich people.
And this is something we don't cover in the course at all, but to keep that in mind in your answer, the question I have is, on that last one, was it statistically significant, the difference between the two? Was that an important thing that you were able to show?
Yeah, so actually I would say that, my thinking and advice has evolved. So the heat map on the General Social Survey was something that we developed in our first Causal Forest paper in JASA. And there we focused, the main point of that paper was the asymptotic theory and the confidence intervals. And so there we just, we estimated the model, we took the model seriously, we took our confidence intervals seriously and tested the hypothesis that those are different. Now, if I was going to go back, we have actually, in that paper, we actually emphasized that coverage of our confidence intervals can be poor in practice. And that's because, especially for people on the boundaries, or if you just don't have enough data, and what basically happens is, again, we don't have enough people just like you, so the estimates are biased towards the mean. So our variances are good, but we're just not able to get an estimate for you that's really centered on the truth for you. And that's really a fundamental problem with nonparametric estimation. It's not special to us. And it means kernels would have the same problem. And people have actually tried to come up with ways to fix it for 20 years and haven't come up with good ways. So now what we would tend to do is before we would take seriously those hypothesis tests, we would first do more calibration exercises. I could take that same heat map, I could actually discretize it, and I could hold out a test set and estimate the treatment effects in each cell separately, and then assess whether my model is well calibrated. The calibration is saying, are my estimates centered on the truth? If they are centered on the truth, then I trust my hypothesis test. But if they're not centered on the truth, if they're flattened, which they often are, especially on the extremes, then I'm not going to trust them. I should mention one other thing that we've done to deal with these biases is we have a paper about local linear forests. And in that paper, we do like a local linear regression. It's basically like a bias correction, because one reason that my estimates are sort of biased towards a mean is that my leaves are not small enough in each of the trees. But what I can do is if I estimate a regression model and understand the relationship between covariates and outcomes a little better, I can do some bias correction to see, like, if you're on the edge of the leaf versus in the middle of the leaf, I can correct for those differences. And so if you're on the edges or the sparse part of the covariate space, that's where you're going to get those biases most commonly. And so the local linear corrections can do quite a bit on the boundaries. It's like, even if you have a very big data set, you still never have enough data on the boundaries, sort of. And so the local linear corrections can help with that. But sadly, they have very bad, they're very difficult computationally. So even though I think they're much better, I don't use them in all of my projects because they're too slow. And that would, speeding them up would be great. Okay, so somebody was asking about bandits. So I guess actually I'll send you guys the slides. I actually had a few slides about bandits. I've been working more and more on bandits in my lab. One of the points that is a simpler point to make is that actually bandit performance itself can be improved using the insights from causal theory, because bandits are trying to solve a causal inference problem, and they're actually creating confoundedness in the data. And that if it's a contextual bandit, I might be giving treatment A more to old people and treatment B more to young people. If I go to analyze that data, either inside the bandit or after the experiment, if I'm not careful, I can bias my own estimates, and those can persist. And actually, you can have failure of bandit performance. And that doesn't contradict existing theory, because existing theory actually assumes you have the right functional form most of the time. But if you don't have the right functional form and you have unbalanced data, you can go very wildly wrong. So we've been working on that problem. We've also been working on trying to estimate policies after using bandits. And so we've developed some new theory around that. So again, you can check out some of those papers on my website. And I've got a little less teaching material on that, but I have some. And then actually, what would be the effect of getting the causal graph wrong, conditioning on the collider, or using it as a covariate? So in general, there's like really just a big division in topics. Like, there's, how do I identify the model? What are my identifying assumptions? Are those assumptions right? And then, there's, how do I estimate my models? In general, the innovations, the computational innovations from supervised machine learning are about doing a good job estimating. And then where the novel insights have been is, well, supervised learning has an objective, and if I give it the wrong objective, it's going to have bad properties. And if I don't do things like sample splitting and what we call cross-fitting in a forest, where we leave one out estimation of nuisance parameters, if we don't do some of those things, then we have bad statistical properties. But the identification part, like, if have you made the wrong assumptions? No, this doesn't help with any of that. And those are really separate things. And in economics, we actually often have separate sections of the paper. Here's the identification section, like, this is about having infinite data. Here's the estimation section. This is what we do. And then we often have a supplementary analysis section where we try to assess the validity of our assumptions by bringing in auxiliary data or finding supplementary facts or implications of theory that would support our assumptions. And so the conditioning on a collider thing is really it's a important issue that's just a separate than the estimation techniques.
And then I think we're at the time that I'm not sure if you have another thing to go to. There's 3 other questions that were above those 2, but we can end here if you need to go. That's fine.
I can take 1 or 2 more. So let's see. Okay, so what if you're not interested in variance estimation? So one of the things that's kind of fun, it's not always true. It would be even more fun if it was always true, and I had a theorem about this, but it's still kind of fun, is that actually the GRF performance, our honest random forests, even in pure prediction tasks, often, but not always, will beat a traditional random forest algorithm. Not always. And so it's worth considering these honest techniques, even if you were not interested in the asymptotic theory. And that's one thing about theory, is sometimes it can guide you to better algorithms. And so some of the weaknesses of traditional random forests are that they overfit to outliers, they do very bad on boundaries, and so on. And so we have sort of natural built-in protections against that in the honest estimation. But there are cases where the performance will be worse as well. So you just don't know. So if you use our GRF package, our performance is as good or better than almost anyone on the web. And so you can try it. We have an option: turn honest on, turn honest off, and see what works better. In terms of in general, though, if you're interested in accurate predictions, you might also open up to neural nets, for example. But again, whether neural nets work better than forests, work better than lassos in a particular setting, it really depends on the context. In a lot of economic data, we have monotonicity properties, like we have structure. Things are smooth. We don't have like an ear over here that we're trying to find over there. So actually, the flexibility of the neural nets can sometimes hurt you. Now, as neural nets actually get better and better at imposing and enforcing and utilizing structure, that trade-off may change. But I would say generally, a lot of our estimators, I didn't get into them today, you can have plug-in estimators where you estimate nuisance parameters like propensity scores with machine learning models. And there it's just a matter of the data set to see what works better. I'll also put out an advertisement for another paper that we've just published on using GANs to create simulated data. And so that's partly to address the problem that we never know the ground truth in causal data. But we use a GAN and we train it again on a data set that we have. Then we create simulated data sets from the GAN where you know the ground truth. You simulate both potential outcomes. And then you can check which of the different causal inferences approach work better using that simulated data. And that's a way to assess. And in our paper, like in some cases, neural nets work well. Sometimes random forests work well. We tried a couple different data sets. And so that's just to say there's no general rule about which one's going to work better. Let's see. So is there something else I missed? R package in Python. Anybody want to build it with me? Come sign up. We have all of the code for GRF is in C++, and we just have an R wrapper around it. And we don't have a lot of funding for this enterprise. So, building a Python wrapper would be awesome. And we just haven't had the resources to do it.
All right. Well, so there's several people thanking you in the chat. Thank you very much for giving this talk and answering everyone's questions.
Great. Thanks so much. It was really great and thanks for all the questions. And sorry it went fast, but again, please feel free to check out my slightly slower paced other resources if you want to learn more. Thanks.